6 cards, numbered 1 through 6, are to be lined up in a row. Find the number of arrangements of these 6 cards where one of the cards can be removed, leaving the remaining 5 cards in either ascending or descending order. Okay. So, somewhat of a combinatorial problem here. If I'm to understand exactly what's happening, we're essentially looking for a sequence of the numbers 1 to 6 such that one card can be removed and the remaining 5 numbers are in ascending or descending order. I want to be careful about not counting repetitions of sequences that do this, right? Because, for example, if I just fill in the numbers 1, 2, 3, 4, 5, 6, I see that if I remove 3, that's in ascending order. But if I remove 5, it's also in ascending order, but it's the same sequence. So my first instinct here was to say, let's start by assuming that the number 1 is the thing that's going to be removed. So then, of course, the remaining numbers are 2, 3, 4, 5, 6. They have to be put in that order from left to right or from right to left. And then we can insert the number 1 anywhere. But that might double count some of the sequences when we then repeat the exercise where, say, the number 2 is the one that's removed. There might still be a way of doing that if we remove the double counting. Another way of doing this is to realize, there are 6 factorial sequences in total. So maybe what we do is we count how many sequences there are, or how many arrangements of the cards there are that do not satisfy this property. That might be more difficult. It sounds like a more difficult thing to directly count. So let's say the number 1. Let's count how many sequences there are where the number 1 is the thing that's going to be removed. So then in the remaining 5 spots, there are exactly 2 arrangements of the 5 remaining numbers. They can either be increasing or decreasing. 2, 3, 4, 5, 6, or 6, 5, 4, 3, 2. And then how many places could I place the number 1? It could go 1, 2, 3, 4, 5, 6 different places. So there are 12 arrangements where it allows for the number 1 to be removed. Now if I do the same thing with the number 2, the number 2 is going to be removed. So the remaining numbers have to be 1, 3, 4, 5, 6, or 6, 5, 4, 3, 1. And where can I put the number 2? Well, if I put the number 2 here, that double counts one of my sequences. It double counts this sequence when the number 1 is put there. And that's the same as if I put the number 2 here, that double counts this arrangement when the number 1 is put there. Are there any other double counts going on? I don't think so. So how many, I mean, there are 12 valid places I can put the 2. Well, for the first row, there are 6 valid places I can put it. 1, 2, 3, 4, 5, 6. But one of those is a double count. In particular, that one's a double count. I can also put the 2 here. So there are 6 places there, but this one is a double count. So what I think I'll do is I'll just remove those double counts. There are 10 places. There are 10 sequences where the 2 is one that's able to be removed, and we satisfy, and we're not double counting. So if 3 is the one that's going to be removed, the other 5 have to be 1, 2, 4, 5, 6, or 6, 5, 4, 2, 1. Okay, so 3 can go, there are 6 places it can go here, and 6 places here. But let's count which of these have already been found. If I put the 3 there, that's already been found, that's already been counted. And if I put the 3 there, it's already been counted. I think also, though, if I put the 3 there or there, it's already been counted, right? Because if the 3 is here, 1, 3, 2, 4, 5, 6, that corresponds to having the 2 put there. So it seems that there are 8 arrangements where 3 is the number that's going to be removed, or that can be removed. And if this pattern continues, we just keep reducing this by 2, right? 12 plus 10 plus 8. Plus 6 plus 4 plus 2. That's 42, I think. 22, 30, 42. Yeah. This is a pretty. This is not. I'm not fully confident in this answer. I would want to sort of work through some extra cases to make sure I'm not double counting more things. What if we work all the way down to the number 6? Then in the last 5 spots, has to be 1, 2, 3, 4, 5. If I put the 6 here, that sequence is already counted. If I put the 6 here, is that sequence already counted? Well, it would have to correspond to, it would have to correspond to the number 5 being the one that gets, the one that is replaced. So it would have come up in my previous list. So this looks like it doesn't work. Okay. So I'll write this as, 6 cannot go there, can't go there. If I put a 6 here, that's fine, it hasn't been counted yet. Hold on a second. But now my pattern doesn't seem to be following. Oh. If 6 goes there, Maybe, hold on, maybe I didn't do this correctly. I don't think this is the way the pattern works. Let's go back to 3. Where can the 3 go? It can go in any of these spots. But which of these have I counted already? Certainly that one. And also that one, right? Yeah. This one has already been counted because that's the standard order. If I put the 3 there, that's already counted from when I put the 2 here. Yeah, so there are 8 arrangements where the 3 can be removed. Let's go up to 4. It might still be, you know, for the remaining ones, it might still be 8. Okay. So that's gone and that's gone because those would be the standard order. And I think those 2 are gone because if I put a 4 right there, then I could remove the 3 and we're still satisfied. But I've already counted all the sequences where 3 can be removed. If I put a 4, if I put the 4 there, I have to remove the 4. And if I put the 4 there, I have to remove the 4. Yeah, okay, so 4 gives us 8 to be removed. If I try the same thing with 5, I do the same thing with 5. So these ones are out. Oops. I wrote these in ascending order. I mean, all the ascending and descending things, it doesn't really matter. There's going to be like a symmetry that applies there. So I can't put it there or there because then we get the standard order, which has already been counted. If I put the 5 here or there, then I could instead remove the 4, and that still works. But everything where I am allowed to remove the 4 has been counted. So if I like if I put the 5 here, I have to remove the 5, and so that definitely has been counted. So there's 8 there, and then for the 6, I think it'll also be an 8. So what do we have here? We have 12 plus 10 plus 8 times 4. I think that this is probably, I I like this approach better than what I'd done before. Just keeping track of, essentially what I've done here is I've figured out all the arrangements where the number 1 is allowed to be removed. And there are, of course, 12 places, 12 sequences where that 1 can go. Then what I've done is I've counted all the sequences which are distinct from the one above, where the number 2 is allowed to be removed as the removal. So of course, if I pop a 2 in somewhere, like here, well, I'm allowed to remove the 1, but that's already been counted. So I'm doing all the ones where 2 is allowed to be removed, but not a 1. And then I have to do the same thing here, all the ones where 3 is allowed to be removed, but not a 1 or a 2. If I put a 3 here, it definitely has to be the one removed. If I put a 3 here, I can remove the 2 or the 4. So the 2 breaks things. If I put a 3 here, I can remove the 2. That's no good. And if I put the 3 here, it has to be removed. Yeah, if I put the 3 here, anything can be removed, including 1 or 2. If I put the 3 there, 2 can be removed, but I've already counted that. Okay. Yeah, so I think this is a pretty good, I'm fairly confident in this, but again, like not 100% sure. This was, combinatorics, this type of problem is not my strong suit. So I'm sorry I don't have like the best explanation for what's going on here, but I've essentially just tried to count all the examples without double counting. If I find a mistake in this though, I'll make sure to include it down in the description. Thanks for watching.